So dear students, now let me discuss about work energy theorem. Okay, in the last class I have discussed about kinetic energy. Now let me discuss about work energy theorem. Okay, and the statement is very simple. Work energy theorem. Work energy theorem. And what is the statement? Statement is that work done, you can say net work done. This is more appropriate word. Okay, net work done on a system or a system of particle is equal to change in kinetic energy of this system. Obviously, change of kinetic energy of this system, and this is a very useful theory for problem solving purpose. Okay, so the net work done can be denoted like this: W net, and that is equal to delta Ke. That means the change of kinetic energy, and delta Ke is sometimes written as K2 minus K1. K2 minus K1. So this is the W net, or you can write it in this way also, because you know kinetic energy K is equal to half mv square. So the corresponding K2 will be half mv2 square and minus half mv1 square. Okay, so this is W net, this is the net work done acting on a system, and this is equal to change in kinetic energy. So you can write it in this way also or in this way also. Okay, and what is net work done? So net work done is W net is nothing but integration the net force acting on the system dot dr. Okay, so this is the W net. Okay, and this F net means what? This means the forces acting on the system. Let me suppose that there are a lot of forces acting on this system, F1, F2, F3. So you have to take always the vector sum of all these. Okay, so that will be F1 vector plus F2 vector plus F3 vector plus dot dot Fn dot dr. So this is nothing but the F net, and we have written here this F1 plus F2 plus F3 in terms of F net. This is the vector sum of all these forces acting on the system or a system of particles or a particular object. Okay, so this is the statement of work energy theorem, and you can prove it easily. Okay, I have discussed in the last class. If you see the video of the previous video of kinetic energy, then you can see that I have defined kinetic energy, and I have done a little calculation that we know the kinetic energy K is equal to, we have discussed that kinetic energy K is equal to half mv square. Now if you take the differentiation of this with respect to t, that is change in kinetic energy with respect to t, that is dk upon dt, just m is constant, so m by 2 into ddt of v square, and ddt of v square means 2v into dv upon dt. So this is m by 2 into 2v into dv dt. Okay, now this 2 will be cancelled out, so it will be just mv dv dt. Okay, so this is dk upon dt, and you know this v into this dv upon dt is the acceleration, so you can write it in this way. So v into just m into dv dt, and this m into dv, the dv by dt is the tangential acceleration, so it will be tangential force acting on the system. This is just ft. Okay, and this tangential force is along the velocity, so they are in the same direction. So you can write it in this way also, that this is ft upon v, ft into v, so dk upon dt. Okay, if you want, you can write this as ft into v. Okay, but if you want to write it in this way also, if the forces is not acting on the tangential direction, then you have to take the dot product of these two. Okay, so in that case what you can write? You can write this dk upon dt is just ft into v cos theta, or you can write it as ft dot v. They are the same. In that case there is no ft, that is f. Okay, because f cos theta is the tangential force, that is along the velocity. If the angle between f and v is theta, then you can write this as f cos theta into v, and this f cos theta is known as ft into v. Okay, so this is the tangential force, this is along the velocity vector v. So you can write it in this way also, with respect to this tangential force ft, that is dk upon dt is equal to ft into v. Otherwise you can write it in this way also, that dk upon dt is equal to f dot v. So this is the more general form than this. So this is just in terms of ft, and this is just in terms of general force f, because it is not necessary that always the force will be acting along the velocity. If the force is acting along the velocity, then this is correct, but otherwise this is the general case, that is f dot v. So in that case what we can write? In that case what you can write? We can write this as dk upon dt is equal to f into dr upon dt. Okay, now you can write this dk in this way. You can write this dk, that dk is equal to just f dot dr. Okay, because this dt and dt will be cancelled out, so this will be dk. So this is the change in kinetic energy, that will be f dot dr. Now if you take integration, if you integrate this expression, okay, so what you will get just integration f dot dr. I have written here from left side. Okay, I am writing this side first, so it will be integration f dot dr is equal to integration dk. Okay, so this integration f dot dr is what? This is the dw. This is the dw. So when you integrate this dw, it will be w. So you can write it in this way also. So it will be just integration f dot dr is nothing but, and this f will be f net also. If there is instead of one force, if there is a lot of forces, okay, there is a many forces acting on the system, then this will be, instead of f, we can write it is f net. So that in that case it will be f net dot dr. So this expression is known as w. Now if you take the limit of this kinetic energy, if kinetic energy vary from k1 to k2, so then it will be just k2 minus k1. If you integrate this dk, then it will be k, and now if you put the limit from k1 to k2, then it will be k2 minus k1. Okay, so w equal to k2 minus k1. And if you write it in terms of velocity, you can write it. So it will be just half m, because k2 will be half m v2 square minus half m v1 square. Okay, so this is how you can, and this is f net dot dr, then you can write it as f w net. So w net will be just half m v2 square minus half m v1 square. So this is actually the statement of this work energy theorem, that net work done on a system by obviously by the net forces. So the work done on a system by any number of force, net work done of a system by any number of force is equal to the change in kinetic energy, or you can say the work done is equal to change in kinetic energy of any system, and independent of the nature of the forces. This is very important. Okay, later on I will discuss about the work energy theorem or something like that, conservative force or the energy conservation, etc. And that will be hold for conservative force. But this work energy theorem is valid for all the forces acting on the system, any kinds of forces acting on the system. It is independent of the nature of the forces. Okay, so this is a very useful mathematical tools, you can say, for this chapter to solve problems, and I will solve problems in the next class. Okay, thank you.